All right. Hi, everyone. Welcome to Machine Learning from Square One. This is the first workshop in a series that we're doing. There's going to be 8 in total this semester, and we're going to be taking a look at BERT and how to build it from scratch, basically using Pytorch and some of the most recent advances in NLP. So these have been really, really influential algorithms in the past few years. And we're going to take a look at how to build how to build BERT from scratch, and some really interesting algorithms for natural language understanding and natural language generation. But we're going to start off today with some of the fundamentals, and that's going to be working with gradients. And in general, what we're going to be doing is understanding how gradients can flow through a model, thanks to the use of data and a loss function, and how it's going to affect the model parameters so that we know how to update them and change them so that the model performs better at a task. In particular, we're going to be using Pytorch for this. So Pytorch is a great library for sort of really hacking around and trying to figure out what's going on in the guts of some of these systems. It's become the dominant language for a lot of machine learning research, so it's definitely good to know. And overall, it's quite intuitive how it changes. If you guys are used to NumPy, Pytorch is a great place to start. It's basically NumPy, but GPU accelerated, and with backpropagation and gradient computations included. So as far as the structure goes for the workshop, the idea is to have around an hour's worth of looking at a notebook together, where I'll sort of run through some of the concepts, and we'll learn some new techniques, maybe look inside some models and work with the algorithms. And then later on, we'll actually sort of play around with these algorithms. You can play with them yourself as you, because the links will be available for the notebooks. And also it'll be sort of a little bit more of a discussion going on. So let's kick off right here. So first things first, we just need to run a few imports and everything. And we'll be using a GPU instance here on Colab. Although right now the computations that we're going to be doing are not really, really intensive. But later on, when we start working with word embeddings and deeper models, a GPU will definitely be useful, and we get it for free here. So before we dive into the nitty-gritty details, let's look at a bigger picture of what machine learning is and how it can be used to solve a particular task. And really, when it comes down to it, there are 3 main ingredients when it comes to a machine learning model, or just machine learning in general. You have your data that essentially includes a series of inputs and outputs, and you have the model that is going to model the transition from those inputs to the outputs. This is why it's called a model, because essentially you're trying to mimic the process that takes the whatever you have as an input. In this case, it might be an image, for instance, digitized into a series of pixels, into a classification of numbers. But really, it could be anything. It could be text, as we'll see in later lectures. But in our particular case, we're going to be dealing with a very simple form of the data that is essentially a straight up and down line, or a sequence of points. These are essentially going to be just points that follow. Basically, you give one number as an input, and you need another number as an output, and that's what we're going to be modeling today. Then you have the algorithm that essentially models the data, and depending on the complexity, you can expect it to perform accordingly. If it's a very complex algorithm, then it will be able to model the complex interactions that can transform the input to the output. And then finally, you have the third element, which is the loss function. And this is essentially a way of telling the model how well it's doing as far as modeling this data, as far as recreating this data goes. Because essentially you need a way of telling the algorithm how well it's doing. And this is what the algorithm is going to optimize, and the loss function is essentially how, when the rubber meets the road, really, how the model is going to learn from the gradients on the data to approximate the transformations from the inputs to the outputs. That's overall what we're going to do. And so to start off with, we're going to do the very simple problem using linear regression, where we're going to use a model that is just going to be a straight line, and we should be able to model our data effectively. So we have our data, we have our model, and now we need to find a way to decide how do we know how well the model is doing. We can use what we call the mean squared error to decide that. And visually what that means, what that looks like is if, say for instance, we have some data points over here. Draw a line. The mean squared error is essentially a way of saying how close are these numbers to that line, right? And we'll take a look, a little bit closer look at this later, but just sort of grasp if you keep in your mind this idea that we already we have an idea of deciding how well that our model approximates the data, then that's all we need. We have the three elements to move on with. And the interesting thing about machine learning is that it's going to essentially take only the data from input to output to decide how to change these numbers, how to change A and B in such a way that they approximate the data as best as possible. And we're going to be using some gradient information for this. Now, before we dive into how the gradients are applied inside a model, in this particular case with the loss function, we're going to just take a look at what it looks like to use gradients in Pytorch. And this code, for instance, handles that just like this. So if one of the prototypical examples for dealing with gradients in general is the f of x equals x squared graph, which kind of looks like this. And the way we could see a gradient, so for instance, if I write down f of x squared, the gradient that we would have here, if everyone sort of knows their gradients and knows how to calculate the derivatives, is 2x at the moment. So in this case, if we want to get information about about this function, so for instance, we might want to get information. Oh, I think your mic is off, Luke. You're not muted. So if we're thinking about the information that we can get from the gradient in Pytorch, we actually get information for a particular point in the graph. So for instance, the exercise that we're gonna do over here is essentially, we're gonna set a point, say we're gonna start with x at 10, right over here, 10, so x equals 10. And we're actually going to try and figure out how to get to the bottom of this graph, the bottom of this hill effectively. And we're going to use, and the way we're going to use the gradient information to do this is essentially to tell us, should we increase x or should we decrease x? And the way we're going to know this is if we know the slope of the graph at a particular point. So for instance, in this case, visually, we can see that the slope is pointing up. For instance, we have a positive gradient over here. And we know this is what we can calculate this analytically, because if we have x over here and we know x is 10, we can calculate the gradient, which would be 20, for instance, in our particular case. If we want to minimize whatever function, we need to go down, we need to essentially reduce that overall value of which is f of x. And the way we do that is by essentially taking the negative, the gradient, and applying this to the new value of x, or as a new value of x. And the way we can, and essentially what that looks like is essentially kind of like taking a step in a direction, really. So we'd be taking, we know we can get the gradient information and take a step in a particular direction to essentially say, okay, well, because the gradient is positive, we need to move in the other direction in order to minimize the function. And so what we're going to do is essentially move a little bit to the left, decrease x, but by how much? And the amount of which that we're going to change, that we're going to reduce x by, is proportional to the gradient itself. So in our case, it's going to be 20. But one interesting thing when it comes to dealing with gradients and trying to minimize them in the context of a function is the fact that you can overshoot. Like you can overshoot by how much you're correcting. So for instance, could anyone tell me in the chat or speak up if they want to, what happens if, like what happens at the next step if we if we apply x over here without modifying the gradient in any form? So for instance, we start with x equals 10, and then we essentially apply the gradient and then keep going. Yeah. So someone said, that's right. So you're just jumping around between 10 and -10. That's the thing. You're doing this effectively. You're just staying in one single place. And we can actually see that because we can actually play around with this right here. So for instance, if we just set this to 1, we run this, and then run this, we actually see the values just hop around between 10 the whole time. What about this? 1.1. What does that look like on the graph? So if we've got anything like this diverges, that's also the correct answer, because essentially we're just jumping up, going like this. Because effectively what's happening is, in this particular case, we're multiplying the gradient. This is what's called a learning rate. We're sort of affecting how much, we're seeing how much does the gradient affect our next step. And here we're saying, well, whatever gradient value it is, we're gonna step 1.1 times that. So we're gonna do a pretty big step. And what that means is, if we take our step over here, we calculate our gradient, which is 20, and we apply we multiply it by 1.1, which is going to be 12. Right, so we're going to do x. We are going to do x equals x minus 12. Oh, no, 2x? Did I get that wrong? I think I got that wrong. No, it's 22 actually. Yeah, so minus 22. 22, yes. And so essentially that's going to give us minus 12, correct? And so this new value over here that we're going to apply to x is going to be around here, which is not going to be good for our graph, because effectively that's going to make us move up and that sort of thing. And that's where this diversion comes through. And if we actually apply this, we can see precisely that happen. So you see it starts off pretty small, but then it just goes crazy beyond, goes all over the place. And then finally, if we actually reduce the learning rate, we're going to essentially take smaller and smaller steps all the way down like this. It's going to take smaller and smaller and smaller. And if we finally run this, this is what it looks like. And so it's interesting to work with gradients in Pytorch in this way, because effectively, this is essentially at the heart of any kind of machine learning code that you'll find online. If you want to modify some information, any kind of sort of structure or play around with new data, you will probably have to understand how the gradients are flowing. Now, you won't have to deal with modifying the gradients themselves or visualizing them, but getting a grasp of how you can simply inspect the gradients is a really useful thing when it comes to working with these kinds of models. So now we've got a little bit of a feel of how to modify a value of x. So just a particular value to minimize a function, and we're doing that by calculating the gradient. We can try and apply it to our problem that we have up here, whereas we're trying to guess how can we change these values in such a way so that this error function that we've decided, which is sort of the distance of the prediction to the actual data, how can we change those numbers in such a way that it minimizes it? Because essentially, just like what we were minimizing before, we're trying to minimize the function f of x. We're going to be minimizing the loss function over here. And this is how we're going to do it. Everyone good so far? Just like say yes in the chat so I can, or let me know if there's something that you guys want to cover as well. Just again, just in case. Because it's a little hard to tell, but we should be all be good. Okie dokie. So let's move on to how we can affect the actual parameters such as A and B in this particular case. So we have our data. We have a particular split of the data over here. And one of the most important things when it comes to dealing with models in general is how you feed the data to these models, because I think a lot of the glamour in machine learning comes down to like sort of designing like really interesting architectures and that sort of thing, and in reality it is that way, but a lot of what it means to sort of be a researcher or handle problems in machine learning that require machine learning is handling data and understanding how to pipe data from one place to another and pipe it efficiently. And one of the ways Pytorch has of doing this is through what's called a data loader. And essentially at the moment, this is a very simple concept, but what we're going to be starting with is essentially just an array of dictionaries that hold the numbers that we care about. So for instance, if we just take a look at the first input, it's just going to be like an array, a dictionary where we have a key, and it's just going to be one of these points. I don't know, like tensor 2. It's probably like this one over here. It's probably like this number or something. That's the one that's what this data point represents. And we can take a look at another one. And essentially the model's just going to get fed a whole bunch of these, and it's going to try and make its best guess how to use these effectively. As far as grouping them together, one of the things we're going to be doing, rather than just looking at a single point at a time, is we're going to be doing what's called batching. And that's essentially where we take, rather than one single point, we're going to take maybe 2 or 4 points all at the same time. And then we're going to take a step to improve A and B based on those 2 points, which will hopefully give us a little bit of a better approximation than just a single point. Because for instance, if you are, imagine you have this point over here, and you have this line, you'd be thinking like, okay, well, from the point of view of the machine learning model, this is, the red line is its current guess, right? The A might be something like, I don't know, negative 0.3, and something B might be something like, 1. We say something like this. With one data point, it's very difficult for the model to understand how to modify this line. Essentially, it could modify it anywhere. One of the easiest ways to modify this is to actually just increase B, really. But in our case, we know that A follows a specific pattern. A is essentially following an upwards trend. So if we have more data points to work with, something like this, then say, for instance, we would do 3 at a time or 4 at a time. I think in our case, we're actually doing 2 at a time, but we can change it up. Once we know 4 points exist, the model actually has a little bit better information to calculate what the distances are between these points. And right here.
Where are you at the moment?
Oh.
Why is it like a clicking sound?
So is it this? I think this is. Let me know if this is unclear for anyone. I'll just go over it. Any questions, by the way, just put them in the chat. So what we're going to, so this is the plan. We're just going to be using 4 numbers at a time, and we're going to collect them all together into this thing called a data loader, and some specific torch functions for doing this is essentially stacking the data on top of each other. So for instance, say we go and do 4 numbers together. We're going to be essentially collecting these samples right here are going to be essentially an array of 4 dictionaries, just like we have over here. And then we are going to essentially collect all the inputs, which we know are tensors. And then we're going to stack them all together. And then we're just going to store it inside this key that is batched inputs effectively. And we can actually see exactly that. And so for instance, the batched inputs that we have right here are 1, 2, 3, 4 numbers, and their corresponding the inputs and the corresponding outputs. So now we have a little bit of information to work with. And as far as the model goes, so in Pytorch, the way we define a model is essentially just like a Python class, effectively. We have to, it has a specific style, so you have to import like you have to subclass it of a module and that sort of thing. But really, this is just all boilerplate, and you get used to it very fast. Essentially, every single model that you might see online is going to have this kind of format. So it will have an initialization where it essentially defines what parameters are going to be used. So for instance, we already know our model. We know it's going to be a straight line. And we know that it's going to have an A that's the slope and an offset. And we're just going to initialize them to some particular numbers, right? So -4 and 10, which is going to be very unsuitable for our task. It actually looks quite similar to our graph right here. It's going to look, I think, kind of like this. That's what it's going to look like, which is not great. So it's going to have to do quite a lot to figure out what the best way is, what the best way forward is. And essentially, now that we've defined our parameters, we just need to define a way to make what's called a forward pass of a model. So this is essentially passing the inputs. Remember at the start, we were talking about transforming data from an input to an output. The forward function is essentially that whole process. You take the inputs, and in this case, we're just defining them for a model. And once we define and run our model, then we've essentially transformed our data. Right now, because the model is initialized randomly, we don't actually. It's pretty bad at generating predictions. We could see, for instance, how poorly it's working. We could, maybe I'll just show them. We can actually explore that later, actually. But essentially, what we're going to be, so now that we have our model, we need to figure out how to train it effectively. And we have our data, we have our model. We just need to define how do we measure how well it's doing. And the way we're going to do that is with what's called the mean squared error, which we've been seeing. And this graph, this little representation that we have over here, this thing is how we're going to. This is what this function is doing. I've just seen a question. Let me just read it. So what is the collate function doing? Is that something that we still want to cover? Finas? Yes. Okay. All right. Let's go a little bit more in depth into the collate function. So the collate function is essentially taking an array of these. So for instance, if we were to call the collate function, this is what it's doing. So essentially we take say collate inputs, and we do, for instance, data set, I don't know, 0. Let's see if we can do this. Yeah, collate inputs. So this is what collate inputs is, just an array of dictionaries that we have over here, and each dictionary contains both the input and target, which are just the X and the Y that we want. And if we pass collate inputs to collate, this is essentially a way of saying, how do you want to group these originally independent samples together into a batch? So the way this looks is essentially we're just grouping these 4 numbers together, and the way we're doing this is by stacking them, because effectively this is what an operation, this torch operation does. All right, yeah. So it seems like all's good. It's kind of frustrating because I can't actually hear when the chat goes up. So we'll just keep going there. Any other questions? Let's see. How do you clarify how epochs affect batch size and so forth? So that goes for overfitting and underfitting, and it might we'll actually take a look at that soon enough, because we'll be underfitting all the time. But then once we get the parameters just right, we'll be able to fit our data. You will see. So let's go into what the loss function is. So essentially, we're trying to reduce the whole problem scope down to a single number that we can try and minimize exactly the same way that we were doing the minimizing of this function here. So essentially, we're trying to reduce everything down. The whole model computation and comparison to the targets essentially needs to be reduced down to a single number. And so if we the way we measure distance here is by essentially doing the difference of the input and the output. So for instance, so we're gonna take what the output of what the prediction of the model is. So whatever the model is predicted here. So like this point over here. I think someone's got their mic off. Could one of the hosts? Oh, I think I want to make one of them co-host. Actually, maybe we'll deal with that in due time. But please put the mic off, because it's actually a little distracting. So let's see. As far as so if we're talking about how to measure the distance, how to measure the loss of the model, we have the prediction of the model and we have the target. And what we're going to do is we're just going to grab the distance from one and the other, and then we're going to square it. And the reason we're squaring it is because the distance could be negative if because we're just doing a difference, especially if, for instance, if we have a point down here, doing one minus the other is going to result in a negative value. And if we square it, it just returns positive, and effectively it gives us the exact same situation that we have here, because we're just reducing, we're trying to minimize the value of something that is squared. And an interesting side property of this is that it means that any number that is really far away, so for instance, this value over here, as opposed to this value over here, so this value is this small value versus this big value. The small value is going to have a lot less influence over the loss than the really big one, because we're squaring those differences, and that's gonna mean the model's really going to pay attention. If there's an outlier, the model's going to try it's going to really try to minimize that error, because it's squared and it's trying to minimize it. So as far as this goes, we can get a value of what it looks like to run. Oh, loss function wasn't defined. We'll just run this. We can see what it looks like. And for instance, right now our loss was probably going to be quite large. Yeah, so 48, essentially, if you take from our batch, so from the numbers that we have over here, if you run it through the loss function, then we get a certain number, and we're going to try and reduce that down. And then the way we're going to do this, similar to how we were doing before, where we essentially taking we're going to be performing a backwards computation with respect to the final output, which what we were doing before was with respect to z, which was x squared. In this case, we're just taking it with respect to the loss, which is the final value number that we're trying to minimize. And this is what this is doing is essentially it's computing the gradients for each one of the values inside of our model. Now, if we visualize what the model looks like, we have essentially, say, x over here. We have A, and then we have B. And so what we're doing is we have a multiplication node over here. And then afterwards, we have a summation node over here. Right, and then we have a difference. So this is for instance our model right here. This little small part over here. And then afterwards, this part that follows over here is our loss. And so what we're going to be doing is we're doing a difference between the outputs. So targets, actually, target goes in here, difference, and then we're essentially doing this squared with another node. Do this squared, and this is our final loss. This is kind of what we're describing. And what this backwards computation is doing is it's saying like, okay, well, I want to compute, you essentially call backwards over here. And this suddenly goes all the way back through the graph and looks at the operations that have been done to the data. Essentially says, okay, well, here you multiplied by 3. So essentially that's going to give a gradient of times 3 at this point. And essentially all the way through, for instance, for addition, adding gradient information doesn't actually flow for addition because you don't, because it's not, it doesn't cause any difference, but it does flow for multiplication. And finally, you get to the values that you care about, such as A and B. And one of the within this whole scope, the things that we can change are A and B. Like these are the values that we can't change. We can't change the inputs, and we can't change the target because that's our data. And so what we're trying to do is we're trying to find A and B such that this loss value is minimized as long as A and B are, because we can see A and B have influence over this computation over here. And so this is the information that we get once we call backwards. We are essentially getting the gradient information for these values right here. And we can see just from computing the loss, we can, for A, we have a specific gradient, and for B, we have another specific gradient. And if you remember as before, the operation that we need to do in order to update the gradient is whatever parameter we have here. Oh, here we go. Whatever parameter P, say, we want to essentially do P minus at this point. And so this is what we're going to be doing. We essentially take our inputs, for instance, we pass them through the model to get the output. So here we're essentially doing this forward computation. We then compute the loss with respect to the targets, and that's this part over here. this section over here. And then finally, we compute the loss, which is, we then say, okay, we'll try and find you the derivatives for these particular points by flowing through this graph backwards, and only affect the parameters of the model, which are the things that we can actually change. Because the rest of the things, like we can't change the x, we can't change the target, but we can change the parameters of the model. And so that's what we're going to do. We're essentially just going to apply the negative gradient to the data, not the data, to the parameters. And we're going to scale that step by the learning rate. And so in this case, our learning rate is 0.05. But as before, if you make the learning rate way too big, then you're just going to be jumping out of this hole. You're going to be increasing the loss if you're not careful. So usually a good practice when it comes down to it is having a small learning rate at the start and knowing that the model is taking its time to find its way down. Let me just read the comments a sec. If we computed the loss function for every point, not only for the sample of 4 points, we get similar outcome as well. Is that the reason we're using only 4 points? That would be much more efficient for a huge data sets. That is exactly right. So for instance, if you can totally do you can definitely do this update, this entire computation on the entire data set. And however, there's an interesting point here, that is, if you compute on the entire data set, there might be situations where you have what's called a local optimum. And I'm sure seasoned people who are interested in machine learning, you've heard the word local optimum before, and probably seen a graph that looks like this. I'll just keep going. And essentially, just like before, if we were going up here and doing our gradient computation, if you start off here, if by any chance of bad luck, your model essentially starts here or the equivalent, whatever n-dimensional plane that this is in, then essentially you're just going to be doing small steps all the way down, and you're just going to find yourself at this point. And it's going to be really, really difficult to get here. It's actually going to be impossible if you just follow the gradient information. And this is actually what tends to happen in really large models, or really really large models with really large data sets, where essentially you have so much, you're trying to take a really correct step by taking a look at all the samples of your data. And so it will take you a really long time to do that computation, because essentially you've got like this huge amount of information to process, but you're really making sure that step is correct. And an interesting thing that happens when that step is correct is that you tend to get stuck in these local optimums. And when you make the batch sizes smaller, so say for instance, if the original data set size is, I don't know, 1,000, and you, instead of taking 1,000, you do batches of 16, then that introduces noise. And effectively, for those 4 samples, that loss function actually doesn't look this way. It looks like this. Right? So for those particular 4 samples, the loss function, if you're over here, it actually makes sense to keep going down and that sort of thing. You will stop over here. Maybe the global optimum is over here. You will stop here. But essentially, you've gotten past this annoying point. And what that means is that if you're using a smaller batch size, it's going to introduce a little bit of noise, and it will actually get you out of those small little local optima. It's essentially a way of, this is really, really helpful when it comes to training these kinds of models, because it's just introducing noise. You're hoping that in general, you will be taking a step in the right direction. It doesn't have to be the most perfect step ever, because actually taking the best step is sometimes counterproductive. So Basil says smaller batch sizes are better. Not always. If your loss, if remember what we were saying before, if you've only got 1 point, then there's going to be too much noise. Then effectively your loss function is going to look like this. Lots of times it's going to look like this, And then the next time it's going to look like this. And the next time it's going to look like this. It's just going to be way too much noise. And your model might eventually converge, but it will take a lot longer and it will just get really confused because it's just saying like, the gradient's telling me to go all over the place. So a balance is good. As far as, so Ina says, you will be calculating the loss for every point just in the batch of 4 at a time. I think it says larger. Yes. Oh, I think, yeah, I think that's the answering the other question. So we can skip that. Cool. So going back to where we were going, we essentially have our loss function. We are updating the gradients. We're updating the values, the A and B over here of our model according to the gradient information that we're calculating. So these green arrows are telling us that, and we're just going to be running a loop over and over. We're just going to be running this over and over, and effectively doing this so many times that those values are eventually going to converge, or at least that's what we're hoping in our particular case. So we'll just create a little bit of information. We'll store these, and once and so, for instance, this is because this is such a small model, it trains really quickly. But over here, if you see this small part, this little point right here is actually where we start. So the way that this graph is structured is, this is the A. This is I'll just draw it in case it isn't obvious. So if we were to visualize what A and B are, so A is in this direction, B is in this direction. These are our 2 parameters of our model. You can imagine for a model that is 1 billion parameters, this graph looks horrendous. It's basically billion dimensions, but in our case, we have a nice simple model. It's only 2 dimensions, only 2 parameters to play with. And so A starts off at -4. Actually, it's the other way around. So B is over here, A is over here. A starts off at -4. So we would say like -4, and B starts at 10. So effectively, our point starts right here. And the target point, which is where we defined our data. So for instance, we defined our data right over here. We already know that the true value of the slope and the true value of the offset are essentially 3. So for instance, the true value is somewhere over here. It's like 3, 3 and 4. 4 and it's 4 and a bit because we're adding a little bit of noise. So it's essentially, this will be like 4.8 or something. So this is our actual target. And so when we scroll all the way down again, this is what the gradient updates actually look like. This is, so essentially we start off at our blue point over here, and then we take a step. And then the next step over here takes to the next place, and the next place, and the next place. And these are all changing numbers. And finally, so for instance, here we're doing 10 epochs and iterating over all values in our data. We'll dive into the training loop in just a second, but just getting the intuition of what's going on. We are actually iterating over all our batches a bunch of times. And then the model is ever so slightly getting closer to these values. And finally, it gets there. It actually gets there. And we can actually see so not only are we seeing what the parameters look like, but this is, for instance, what it looks like when it comes down to actually visualizing the slopes. Because effectively, the model might start off with this line down here. And essentially, it's slowly being brought up and that sort of thing. And you can see that the model over here is actually spending quite a lot of time. It's spending quite a lot of time over here in the middle, because changing B is actually a lot faster than changing A is. Just because that's how the slope, this 2D slope that we're going down is shaped. It's quite abstract to imagine, but imagine this landscape right here, this 2D landscape of the parameters is essentially curved down, and this is a ball rolling down a hill. And it just turns out that changing B, the slope that changes B is a lot more apparent to the model than the slope that changes A. And so it essentially converges down that way, and B changes faster than otherwise. Question. So in this example, what are you using to find as mini batch gradient descent? Yes, that is correct. Mini batch gradient descent. No, so stochastic. So these are so stochastic means essentially you're taking these at random. You're sampling from the data set at random. Here we aren't sampling at random. We start off with a random array of inputs and outputs, and we sort of just cycle through those. In practice, it doesn't actually matter too much. If you want to maybe add a little bit more noise, as for the same reason that we were describing before, to help the model get out of local minimum and that sort of thing, it might be useful to do sampling. But effectively, what we are doing is mini batch gradient descent with an initial random seed, but we aren't sampling stochastically from the data set. Everything good so far? Because we'll soon get our hands dirty with some coding. And so now we've got our information. We've been training and that sort of thing. The only thing that we're doing in this loop, really, because all this is just plotting and saving the values so that we can actually see them and that sort of thing. The rest, this is just matplotlib sort of stuff. This training step, all we're doing is just calling the training step a whole bunch of times with a new batch of data and the same model. That's all that's happening. And the model, essentially, we just take the model, we pass the parameters, we update them, we set the gradient back to 0. That's an important part, because if not, we're just going to keep stacking the gradients, and it's going to basically be really, really noisy. But one of the coolest things is to understand what it looks like when we play with the learning rate. So does anyone want to take a guess at what this graph over here is going to look like if we set the learning rate really low? Let's set it to this. It's going to take forever, but is it going to? So here you're fine to switch on the microphones if you want to, and just tell me what it's going to look like, because maybe like the interaction will work better. If not, that's all right. I'll just read the chat. Maybe it won't even get to the actual value of A and B. That's a very good guess. Very good guess. Let's actually run it. Actually, we need to restart. We need to reinitialize the model. Essentially, we've already set the values. If we can take a look at what the model parameters are. And yeah, we're not really going anywhere. We start off here, and the value is just so small. There's a little bit of movement, but it's so tiny. Let's see what happens if we make this a little more. It's doing something. It's taking like really correct steps. If we reinitialize the model again, and we just change the learning rate again. That's getting better. And we already know what happens here. Yeah, it just goes there. Who wants to guess what it looks like when the learning rate is too high? Now, the intuitive answer is essentially it goes all over the place, but maybe a little bit more nuanced than that. Who wants to give a little bit more nuance? Like, what if we set this to, I don't know, 0.5? What is this going to look like? All right, last few seconds to answer. Oh, I think it actually manages to get there. We take a look at this. it's tricky. I think it's actually really difficult to tell what the parameters are. We can actually see what the model parameters are. So for instance, if we add some more code over here, model A. Oh, interesting. So nan, this is basically an overflow. The values got so big, the gradient information was so big and so out there that the values overflowed. So we definitely need a little bit less. If the values are nan, that's not going to help. So we need to reinitialize the model. Yeah, and we're there again. The interesting thing is, if we start from a different point, if we start, say, from instead of plus -4, we start, say, 4 and -10, this is effectively a different starting point for the model. And we can effectively see what that looks like on the graph. So this is starting down here, and it goes all the way back up again. So it doesn't actually matter, but this is kind of what the landscape looks like. And finally, these are what our outputs look like, a little bit all over the place. And then finally, we can make predictions with our fantastic model that can predict a straight line, which is excellent. This is all what machine learning is about, looking at lines and numbers. And so finally, when it comes to working with models, we don't actually define each individual parameter like we do up here. This would be incredibly tedious to do. And so as a shorthand, one of the things we have are what's called dense layers. And these are essentially, this is exactly the same thing. So for instance, if you imagine A and B being, so A is a linear transformation of space where essentially you're rotating space or shifting space along the x-axis, and B is a sort of a shifting of space, essentially you're a translation. It just turns out that the dimensionality of our input is sort of one-dimensional, because essentially you were just dealing with one single number. So the translation is just the same thing as adding. But in a 2D space, you can add two numbers and transform space using a 2D matrix. And effectively, this is you've probably seen like what these standard neural network diagrams look like. This is kind of what they mean. This is effectively the nodes aren't actually the numbers. They don't. The way to read something like this is the weights that are inside the model are actually the connections between the nodes. And effectively, if you have a node, if you have a series of nodes over here, 2, 3, 1, 2, and so on, like this, these things are sort of just placeholders. The things that actually contain the numbers are these. So this would be like A1, A2, A3, and that sort of thing. These are our numbers. In our case, we just have a single placeholder, which is where X is. We multiply it by A, add B, and then we get our output. But we can imagine we would have maybe multiple inputs. So for instance, if your input is two-dimensional, you could increase it to say two A's, and then over here, two different types of A's, two multiplications, and then one single B, which makes sense because if you sum these two numbers together, then you are essentially, you only need to add one. You only need to add one number. It wouldn't make sense to add two numbers in this kind of diagram. And there's a really interesting, there's a really nice way of representing these linear transformations, and that's through matrix vector multiplication. And this is what is at the heart of any kind of dense neural network. It's just a series of matrix multiplications, because effectively all you're doing is you're taking your input, which is just X, which would be a vector, like multiple X's over here. And you're essentially applying a series of weights to them. You're multiplying each one and having them interact in specific ways defined by these matrices. And then you're receiving a specific shape as an output. It can either condense down into a single number or it can spread out into a whole bunch. This, for instance, this matrix, this diagram over here, say for instance, we have 2 inputs and we actually want to expand this out to say 3 inputs, for instance, over here. This sort of thing. This is effectively, you have your input over here, which is x1, x2, x1, x2. This is your vector. And the matrix is effectively going to be, so this is what's called a 2 by 1 or 1, yeah, 2 by 1 matrix, because there's 2 rows and 1 column. And here you would have a 2 by 3, no, 3 by 2 matrix, which would essentially contain different numbers over here for your A's, like A1, A2, that sort of thing. And this essentially is transforming, you're essentially casting this 2-dimensional vector, this 2-dimensional point into a 3-dimensional space. You're effectively sort of, imagine having a plane in space, sort of in 3D space. Imagine a plane cutting through space. You're essentially mapping that 2D input, which is here, into a 3D point. And of course, if you want to do like the plus B over here, B needs to be a 3D vector, right? Because the output of this is going to be a 3 by 1, as per traditional matrix multiplication. And so usually when we think about these, when we think about dense layers and that sort of thing, we're thinking about matrix multiplication. And this is how we, sorry? Oh, never mind. And so this is how we see, this is how we define, for instance, a 1 by 1 matrix multiplication, exactly what we had before, A and B. So for instance, we make sure we have a bias set to true, but effectively all we have is, if we can actually inspect what's inside the linear layer over here. Oh wait, it's over here. It's over here already. So for instance, the linear weight data is a 1 by 1 matrix, and then the bias is just a one-dimensional vector, and that's what we're seeing. And so the task that I'm going to give you guys, and the one that my lovely tutors are going to help everyone out with, is essentially to make the same model that we've made before. So the one that we used to do this, using all the information that we have up here, you essentially need to define a new model with this linear layer. And for instance, just to give you an example of how this works, this essentially gives you the result. If you give it a single number, like a particular input, it will spit out a single number as well as the output, as per we've specified over here. And it essentially is just multiplying the input by the weight and then adding a bias. And so that's what we're going to do. How did everyone find that? Is it all making sense, or is everyone like really intimidated about trying to tackle this challenging problem? All good? All good. That is excellent to hear. So what we're going to try and do just now is break everyone up into different rooms. So this is kind of the first time I've done something like this.